Welcome to Derectronic, where we experiment, learn, and build with electronics. What are multivibrators? In the world of electronics, these are circuits used to generate, store, or process pulse-type waveforms, examples of which are square waves and rectangular waves. Some of its key applications are as follows. It's used in timing circuits when it is in astable mode. It's used in signal shaping and pulse generation when it is in monostable mode. And it can also be used as a memory storage when it is in bistable mode. For today, we will be building an astable multivibrator circuit. An astable multivibrator circuit is also called a free-running multivibrator. Why is that so? You will find out later on this video. Some of the key applications of this type of multivibrator are as follows. It's used in clock pulse generations, so timers and oscillators of computers have them. It's used in flashing lights, so LED blinkers, warning signals, uses astable multivibrators. It's used in signal generators. These are normally found in radio equipment. And it is also used in pulse width modulation, which you would normally find in communication systems. The main component of our astable multivibrator circuit today is the 555 timer or 555 integrated circuit. Given that this is an integrated circuit, let's take a look at its pin configuration. So the pin configuration of the 555 timer looks like this one on the diagram on the right. As you can see here on the diagram, it looks similar to our LM741, which is our operational amplifier, the one we used in our previous video. It has 4 pins on the left, 4 pins on the right, and the pin configuration is exactly the same as that of our LM741, wherein you have to find a notch, that rectangular notch on one side of the IC, so that you will have that one. You use that notch as a guide to figure out where is pin 1, 2, 3, 4, 5, 6, 7, and 8. Now, in terms of application, where do we use the 555 timer? Now, this integrated circuit is actually used in a variety of timers, delay, pulse generation, and oscillator applications. This makes it perfect for use in multivibrator circuits. The schematic diagram of our astable multivibrator circuit utilizing a 555 timer would look like this. As you can see in this diagram, we have the 555 timer here at the middle. Let us interface the pin numbers in the diagram. There. Now, as you can see here, okay, pin 1, which is the ground pin of our 555 timer, and pin 8, which is the VCC pin of our 555 timer, will be connected to ground and the positive terminal of our power source, which is a 5-volt DC supply source, respectively. The output, which is pin number 3 of the 555 timer, will be connected to a 220 ohm resistor, R1, and that resistor, which is actually serving as a limiting resistor, is connected to the anode of our red LED, with the cathode of that same LED connected to ground. Now, there are 2 more resistors here on the left-hand side. As you can see in this diagram, R2, which is a 10 kilo ohm resistor, and R3, also a 10 kilo ohm resistor, are connected in series. And we also have a capacitor here below, a 100 microfarad capacitor, also connected in series with the 2 resistors. Now, that branch, okay, is connected to the 5-volt DC supply. In particular, the R2 is connected to the 5-volt DC supply, while the negative terminal of the capacitor is connected to ground, as you can see here. Now, the other pins of the 555 timer are connected as follows. Pin number 4, the reset pin, is connected to the 5-volt source. Pin number 7, the discharge pin, is connected in the junction between R2 and R3. The threshold and the trigger pin, that will be pin 6 and pin 2 respectively of the 555 timer, is connected in the junction between R3 and the capacitor, the 100 microfarad capacitor. And as you can see here also, on pin number 5, this is the control pin of our 555 timer. There's nothing connected here. Actually, that control pin is optional. I'll explain that in the next slide. Why is that so? Now, the oscilloscope connection is also shown here. Okay? Most common connections are as follows. Okay, you see the negative terminals of both channels connected to ground. That will be the common pin in our COM3 lab protoboard connected to ground. Channel A, the first channel of our oscilloscope, is connected to the output, pin number 3 of our 555 timer. Channel B is connected in the junction between R3 and our capacitor. What is being measured here? If I do something like that, what is actually being measured on channel B is the voltage across the capacitor. So what we'll see on channel B is the waveform of the capacitor voltage. Now, what do we expect to see once we turn on our COM3 lab protoboard and the oscilloscope here in the circuit? Now, this diagram on the left will somehow explain that. Now, on our oscilloscope, channel A, or in particular, that would be the Y1 channel, we will see a square wave like this one. Okay, so we have the square wave that will be pulsating from 0 to a high value. Now, when the waveform or the square wave is at 0, we expect the LED to be off. When the waveform is here at this high value, we expect the LED to be on. Now, how long will the LED be on and off will be dependent on the value of R1, R2, and the capacitor. I'll show you the formula later on. Now, our second channel is connected here at the capacitor side of the circuit. Actually, between R2 and the capacitor, it's connected here. Now, what do we expect to see now at the Y2 channel of our oscilloscope? We will expect to see something like this. As I mentioned on the previous video, what you will see on the Y2 channel is the capacitor voltage. Okay, now the curve going up represents the charging of the capacitor, and the curve going down represents the discharging of the capacitor. So the capacitor in this circuit is actually charging and discharging, okay, at the rate, okay, based on its RC time constant. Now, the charging and the discharging time of that capacitor will determine when the LED is on and off. How is that? The diagram here on the right illustrates it. As you can see in this diagram, okay? So once you turn on the circuit, the capacitor will start to charge. When the voltage on the capacitor reaches around 1/3 of the supply voltage, if you have a 15-volt source, that would be 5 volts. If you have a 5-volt source, that would be around 1.6, 1.7 volts. So once the voltage on the capacitor reaches around 1/3 of the supply voltage, the capacitor will, the LED will turn on. Why? Because the capacitor at that point now is on this waveform, or this rising edge here, okay, this curve. So during this curve, on the charging time of that capacitor, okay, the LED is on. Now, once the capacitor voltage reaches around 2/3 of the supply voltage at this point, the capacitor now will start, after that, the capacitor now will start to discharge. As you can see through this curve, start discharging. And during that time, while the capacitor is discharging, the LED is off. So as you can see in this diagram on the right, during the charging time of the capacitor, the LED is on, and during the discharging time of the capacitor, the LED is off. Now, how long is that charging and discharging time? It could actually be represented, the value of that can be actually computed using the following formulas. Like, for instance, the off state, this one, T2. The off state of the output waveform can be computed as follows. T2 is equal to 0.7 multiplied by the value of R2 multiplied by the value of the capacitor. This value is measured in seconds. The unit of this one is in seconds. Now, the on state. How about the on state of the LED? How long will that be? Again, that can be computed similar to the off state. That will be T1. So to compute for T1, we have this formula. So T1 would be equal to T2, the result of this one, the formula here on the left. So it will be T2 plus 0.7 multiplied by R1 this time around, the value of R1, multiplied by the value of C. Let us now construct our Astable Multivibrator circuit using this COM3 Lab protoboard, just like what we did in our previous video. The NE555 Timer Integrated Circuit I've already inserted here on the breadboard. As discussed earlier, the pin configuration of our NE555 is very much similar to our LM741, the operational amplifier integrated circuit we used in our earlier videos. The notch I'm referring to in my earlier discussion is actually located here on the left side of this IC. Now, the notch is actually facing here on the left. If that's the case, just like our LM741, pin number 1 of the 555 will be here on the lower left-hand side. Then going to the right, you get pin number 2, pin number 3 here, pin number 4. Pin number 5 will be here on the upper right-hand side. Then going to the left, you've got here pin number 6, pin number 7, pin number 8. Now, for starters, what I'll do, let me first establish the positive 5 volts and ground connection for our circuit. Based on the schematic, we are using a positive 5 volt power source, DC power source for this circuit. So if that's the case, I will be using on the protoboard these 2 pins, okay? The positive 5 volts here and the ground here on the fixed power supply section. Now, so I'll put a red wire on 5 volts here first. And I will establish now here on the breadboard, where is this 5 volt or this line, 5 volt line will be connected. I'm going to use the top power rail here at the top, the red side of the top power rail. There. So from there, I've established now that the top power rail, red side, will be our 5 volts. For the ground, let me connect another wire, second wire, to the ground here. Ground, I'm going to use now, this time around, the bottom power rail. The blue side I'm going to use. So let me just do that. I'll insert it to the blue side. So here, the bottom blue power rail will be our ground. Now, if that's the case, let us now connect the ground pins and the VCC pins of our 555 timer. Based on the pin out configuration, ground is pin number 1. Pin number 1 is this one, pin number 1. Okay, pin number 1 should be connected to ground. Let's do that now. Pin 1 of our IC, integrated circuit, will be connected to ground here. Okay, and pin number 8 at the top here. Pin number 8. Pin number 8 here. I'll connect this one to our positive 5 volt source here at the top. There. Pin number 8 to positive 5 volts. As you can see there. Pin number 8. Okay, now let's now establish the output part of our Astable circuit, Astable Multivibrator. On the output pin of our 555 timer is pin number 3. This one, pin number 3. On the output, based on the schematic, I would need to connect a 220 ohm resistor. I have it here. How do I know this 220 ohm resistor? You have to take a look at the color on the body. I'll refer you again to my resistor color code video in my channel in Derictronic, at Derictronic, okay, for reference. So 220 ohm resistor to be connected on pin 3. Let's do that now. 220 ohm resistor connected to pin 3. The other leg, one leg to pin 3, the other leg to a free pin, somewhere on the right. And that other leg connected on the free pin will have to be connected to an LED. Which side of the LED? You have to connect it on the cathode side. That will be, anode side of the LED, the longer leg. Here, the cathode will be grounded based on the schematic. So let me connect now the anode to the other leg of the resistor, like so. Do it properly, there. Okay, the cathode of the LED, which is here on this side, okay, I need to connect it to ground. Okay, let's do that now. Cathode of LED to ground. Here. Cathode of the LED connected to the ground rail, blue, bottom blue rail. Okay, now that establishes our output. Now, pin number 4 of the 555 timer, based on the circuit we have earlier, okay, is to be connected to 5 volts. Let's do that first. So pin number 4, I'll connect pin number 4 of the 555 timer to 5 volts. There. Pin number 4, connected to 5 volts. And for the other components, let's do that now. Okay. Based on the schematic, we will be needing two 10 kilo ohm resistors. I have them here. 10 kilo ohm resistors. These two resistors have to be connected in series with one resistor connected to positive 5 volts. Let's do that now. So one resistor, one of the 10 kilo ohm resistor, I'll connect it to 5 volts. The other leg, I'll put somewhere here on the free pin here. On the side. There. 5 volts connected, free pin here. The second resistor, 10 kilo ohm, I'll connect it in series with that resistor. So resistor here. The other leg here, free pin. There. In series. Now, this leg of this resistor, the second resistor, will have to be connected to a 100 microfarad capacitor. I have it here. Which leg? Okay. Remember, our electrolytic capacitor has a positive and a negative leg. That resistor leg, the second 10 kilo ohm resistor, will have to be connected to the positive terminal of our capacitor. That would be the longer leg. It's this one, this leg of the capacitor, this one, longer leg. The negative, the shorter leg of the capacitor, will have to be grounded. Let's do that now. So longer leg connected to the resistor here. Shorter leg on the ground. Shorter leg on the other side, like so. Let me just transfer the leg of this resistor. Once, yeah, somewhere here. Okay. Transfer the capacitor. There. It's not too squished. Okay, there. Okay. Positive capacitor connected to the resistor. And the other leg of the capacitor, negative terminal of the capacitor, I need to ground it. Okay, let's ground that leg. Have it there. Grounded. This is here. Okay. Now, based on the schematic, okay, connection something like this. As for the other pins of the 555 timer, okay, according to the schematic, pin number 2, here, I connected a jumper wire there, pin number 2. Pin number 2 of the 555 timer we need to be connected to pin number 6. Let's do that now. Pin number 2 to pin number 6. There. Pin number 2 to pin number 6. And pin number 6, the other side, okay? Pin number 6, so let's have another jumper wire on pin number 6. Here. Pin number 6, another jumper wire on pin number 6. Okay, we'll have this wire, the second jumper wire coming from pin number 6, will have to be connected in the junction between the capacitor and the second resistor, 10 kilo ohm resistor. Okay, let's do that now. There. Have it there. Okay, pin number 6 to the junction between. Pin number 7 of our 555 timer, this one. Pin number 7 for 555 timer. Will have to be connected via a jumper wire again. So let's have another jumper wire on pin number 7. Put it here, pin number 7, there. This jumper wire coming from pin 7. Okay, so from pin 7, second jumper wire, this jumper wire will have to be connected to the junction between the two 10 kilo ohm resistors here. Let's do that now. Connect it here. There. Actually, that more or less completes our circuit connection, frankly. Okay, I could actually turn on the board right now and observe the red LED as I turn on the board. Now, with the board switch on, as you can see here, so I switch on the board from here, the top first, here. Then I switch on the power supply, fixed power supply from there, from here. Now, with the board switch on, you could actually observe the red LED. It's blinking here. Okay? The blink rate of that red LED, based on our theoretical discussion earlier, is dependent on the values of these two resistors here and the value of the capacitor. Okay? The rate of the blinking is actually based on that one. Okay? Now, the length of when the LED is on and off is actually totally dependent on the charging and discharging of the capacitor here. So, and that charging and discharging time is based on its time constant, the RC time constant. So, if that's the case, if I change the capacitor to something, let's say a lower valued capacitor, I have a 100 microfarad capacitor here. If I change this 100 microfarad capacitor to a lower valued capacitor, you would expect the blinking rate of the LED to be faster. And inversely, if I change the capacitor value, this one, let's say to a higher valued capacitor, you would expect the blinking rate of the LED to be slower. Now, what I'll do is this. I have a couple of capacitors here. I have this one is a 47 microfarad capacitor, and I have another one here, which is a 10 microfarad capacitor. What I'll do, I will replace that 100 microfarad capacitor with this one, and try to observe the red LED, the blinking rate of the LED as I do so. See the blinking rate of this LED, okay? If you could actually count this, a little over 1 second, maybe 1 or 2 seconds from the time it's on. Now, let's see now if I replace the capacitor. Okay, let me switch it off first. I'll replace the 100 microfarad capacitor first with the 47 microfarad capacitor, this one. Let's do that now. There. 47 microfarad. Let's switch this on now. Observe the blinking rate of the LED. It's faster than before, than with the previous circuit, compared to when I have a 100 microfarad capacitor here. Now, again, let's replace again that 47 microfarad capacitor with the lower valued one. This is a 10 microfarad, this one. Let's do that now. I'll switch this one off first. Let me replace the capacitor, this one. Okay, 47 microfarad, I have it there on the board. Let's replace it with the 10 microfarad capacitor. 10 microfarad, there. Okay, I'll switch this on again. See the blinking rate of the LED is faster. Because I've said, okay, the time the LED spends on its on and off state is dependent on the charging and discharging rate of the capacitor. The higher valued capacitor will charge and discharge longer compared to a lower valued one. I'm referring to the capacitance value, the farad value of the capacitor. Okay, so with the 100 microfarad capacitor, it's slower. First one, the original capacitor. And with this one, this is a 10 microfarad capacitor. This is actually 10 times lower than the original capacitor. See the blinking rate. It's a lot faster. So let me switch this back. Switch on. I'll return the original capacitor, our 100 microfarad capacitor. Here. Oh, let me just fix the legs first. There. I'll connect it again. Oops. Let's fix the legs first here. Connect them. There. She's on. So this is the original blinking rate we saw earlier. Original, okay? About 1 or almost 2 seconds interval. Okay, now to observe the capacitor voltage compared when compared to the on and off state of the LED, we need to connect our oscilloscope to the circuit. So based on the schematic, okay, Y1, which is channel A, will be connected to the output. Okay, so the output is pin number 3. So I need to connect Y1 channel of the oscilloscope to the output. Okay, let's do that now. Pin number 3 here. Careful there. That's pin number 3. Y1. Y2, the second channel of our oscilloscope here. So I'll connect another red wire. Y2 here will have to be connected to the junction between the capacitor and the second resistor, okay, which is here, where our pin 6 wire is connected. Okay, so junction between the capacitor and the second resistor, 10 kilo ohm resistor. So let me connect it here. Careful a second. Oops, let me just do this one carefully. I don't want to damage the component. There. Okay. Junction. Okay. Have a closer look at that one. Okay, see there. Okay, so this one on the output, Y1, Y2, junction between the second resistor, second 10 kilo ohm resistor, and the capacitor, so that we can observe the capacitor voltage. Now, the COM connection which is the common wire, the common terminal of our oscilloscope, will have to be connected to ground. So I'll connect it here, all the way here, down, blue rail, bottom blue rail, there. Okay, with the oscilloscope connected, let us now observe the waveforms generated by our Astable Multivibrator circuit. With the oscilloscope of the COM3 Lab protoboard wired properly, let us now observe the capacitor voltage and output waveform of our Astable Multivibrator circuit. To do that, let's open first here on the companion software of our COM3 Lab protoboard. Let's open first the oscilloscope here. We put the display here on the right hand side, make it bigger, like that. There, okay. I'll switch on Y2 because I have something connected in the Y2. Let's see a preview first before I start adjusting. Okay, I'm going to click preview first and I'm going to run the oscilloscope. Okay, I think the waveforms are too wide, so I need to change the horizontal time division setting, okay, to a higher value. Let's put it at 200 milliseconds first. Let's see what happens. Still too wide. Let's put it at the 500 milliseconds, highest setting possible. There, okay, to be better. Okay, now the square wave you see here, let me just put it here a little bit closer. Okay, here. The square wave you see here, the black one, that's our output waveform. The one connected in pin 3, that's Y1. The blue one, you see this horizontal, that slanted line, that's our capacitor voltage waveform. That's on Y2, the blue line, okay? Now, okay, now based on our theoretical discussion, okay, let me just put this one first. Let me make it on one sweep. Let's do this one first, okay? I'll set this one to Y1 trigger, and I'll make it just one sweep. So that's it again. Here. Okay. According to our theoretical discussion, okay, you could actually see it here. It's very clear here. Okay. That slant line going up represents the charging time of the capacitor. Okay, that slanted line going down is the discharging time of the capacitor. As you can see here, when the capacitor is charging, the output is high, or the LED is blinking. When the capacitor is discharging, the output is low. The LED is in its off state. Okay, so charging time, capacitor on, discharging time, it's off. Based on our theoretical discussion, okay, the charging time of the capacitor, okay, LED will turn on once the capacitor voltage reaches 1/3 of the supply voltage. Our supply voltage is 5 volts, so 1/3 of that is approximately around 1.6, 1.7 volts. We could actually confirm that here, okay, by using the vertical, one of the vertical cursor. Okay, let me put it on the lower part of the here, there. Okay. Now let us now check the position of that cursor, the red one. Okay, see, it says here 1.69 volts. Okay, that's 1/3, approximately 1/3 of the supply voltage, which is 5 volts. Now, based on our discussion also, okay, once the capacitor reaches 2/3 of the supply voltage, it will start to discharge. Let's verify that, okay? I'll put this here at the top portion, there, red one, okay, at the top portion of that slanted line, the blue waveform, our capacitor voltage. And let us now see the position of that red line. Okay, see this one. It says here 3.25 volts, okay? 2/3 of 5 would be around 3.3, 3.4 volts, okay? Approximately. 2/3. Okay, so when the capacitor voltage reached 2/3 of the supply voltage, it started to discharge. Now, the length of time of the on and off state of our astable multivibrator circuit can also be determined through a formula. Okay, now to verify that, what we need to use is now the horizontal cursors of our oscilloscope. These two. Okay, so we have a blue and a red one, the right hand side here. So what I'll do this one, okay? Let me do something like this, okay? I'll put the horizontal cursors first, okay? Between so that the position of so that the blue and the red will be so the on state of our LED, the LED state is on in between these two vertical lines. Vertical line, see there. Okay, now, so the capacitor started charging from here and the capacitor started discharging from here. So in between the red and the blue vertical line, we have now the on state of our LED. Okay, now, this, how long is that? It's actually measured in seconds. You could actually compute it from here. Okay, see this one? X red, X blue. X blue is a position of this blue cursor. X red is a position of this red cursor. So I have 2.67 seconds for X red and 1.22 seconds for X blue. So if I subtract those two values, I'll get the time, okay, spent by the LED while it's on, okay? So that would be 2.67 minus 1.22, around 1.45 seconds on state. So 1.45 second on state. Now the off state, I could compute it from here. Okay, I'll position the red, the blue here. So around 1.45 for the on. Huh? Okay, now blue here and the red will be somewhere here. When the capacitor started to charge, okay? So here. So at this, between the red and the blue vertical lines, okay, we have the off state of our LED. Now, again, I can compute for that, how long is that one, okay? Through here. Okay, you see X red is 1.23 seconds, it says here on our oscilloscope. And X blue is 520 milliseconds, that's 0.52 seconds. So I have 1.23 minus 0.52 seconds, I've got 0.71 seconds. 0.71 seconds. So approximately 0.7 seconds off and a little over 1.4 seconds on. Let's verify that, okay? As I've said, we can compute for that, and I actually showed you the formula to use to get that computed. I have a calculator here. We could actually compute for that. So to compute let's compute for T off first, the off state. According to our oscilloscope, it's 0.7 seconds, 0.71 to be exact. Okay, now the T off state is computed as follows, okay? The formula is 0.7. Let me just switch on my calculator first, okay? The formula is actually 0.7 multiplied by the value of the capacitor. So our capacitor is 10,000 ohms, okay? So 10 kilo ohms, that's 10,000 ohms. 10,000, okay? Multiplied by the value of the capacitor. We have a 100 microfarad capacitor in our circuit. So that will be 100 times 10 to the minus 6. I have it there. 100 times 10 to the minus 6. Now, if I press equals, what do I get? 7 over 10, like this. You see there. I'm getting 0.7. Okay? This is a computed value. And our oscilloscope, in our measured value, is saying 0.71. So it's very close to our measured value. Okay, now, to compute for the on state, how long is the on state? I also gave you the formula in the theoretical discussion in the video earlier. Okay, so according to the oscilloscope, the measured value is 1.45 seconds, around that value. Okay, let us now get the computed value of the on state of our circuit. So the formula is this, okay? To compute for T on, the period on, okay, I need the value of T off, so that will be the previous answer, plus 0.7 times the value of the capacitor, the value of the resistor first, 10,000. 10,000 here, okay? Multiplied by the value of the capacitor, which is 100 microfarad.
minus 6. There. Now take note, okay? In the first formula, you have to use R2. In the second formula, you have to use R1. Since in our circuit, R2 and R1 is the same. It's both 10 kilo ohms. So I'm just using 10,000 ohms for both formula. However, okay, if the two resistors, the two resistors connected in series is of different value, take note, okay? The first resistor is the one connected. The first resistor is the one connected on VCC, okay, on the 5 volts. The second resistor is the one in series with it. So don't make a mistake because your computation will go wrong if you do so. Okay, so this is now for T on. Let's see the value computed one. Okay, 705. What do I get here? See. Okay, see. Based on my calculator, computed value, I'm getting 1.4. 1.4 seconds on computed value. And on my measured value, I got around 1.45. Very close to the measured value. Okay? That more or less confirms the theoretical aspect of our discussion earlier in this video. Now, with that, I would like to bring to a close this video on Astable Multivibrators. And as always, I would like to encourage all of you to keep experimenting, keep learning, and I hope to see all of you next time here in the Electronic.